recording. So let's start it again. And so we'll look at virtualization and see how it affects cloud computing. Also look at different mainstream virtualization technologies, and then also look at giving you a brief introduction to virtualization. Right. So from the objectives, as I said, we looking at the essence value of virtualization. Also understand some mainstream virtualization technologies that's out there, look at the difference between them, and also understand the basic principles of how these operate. So first thing, as I said previously, we look at virtualization as the foundation. So as I said earlier, if you had like three different PCs here, for instance, they are all isolated from each other. So which means that one is on its own, that one is on its own, that one is on its own. It means that if something goes wrong in Ubuntu or Red Hat, they all go down. And this is where we talk about virtualization creating an abstract layer, removing the tight coupling between physical hardware and operating systems. And so this is where we're moving towards, or what we currently have, which is now the virtualization layer that's created, that's here. And so the virtualization layer sits on top of your hardware, and your hardware, it's your CPU, your RAM, your graphical user GPU card, and your hard disk. And that sits there to make sure that your hardware gets set, almost like you create a resource pool. And so the resource pool means that all your resources, physical resources, are virtualized to a set resource pool, and then your operating systems are decoupled. So they're not tight coupled like previously, like this here. They're decoupled from the hardware, and the resources are all allocated, from that resource pool. And this is where we have this talk of, I think in the past we heard about VMware. So you have VMware, you have VirtualBox. So these are all, the ones that you normally use on your PCs, right? Oracle VirtualBox. There's also others out there. And so again, the virtualization layer is allows you then to share the CPUs all together. As you can see there, all the memory together, all the GPUs together, all the disks together, right? They're all set as one resource pool. And then when you need to create a virtual machine, you use the needed resources that needed for a virtual machine. So when you look at the setup here, and I know sometimes when you have a server, you sometimes want to go overboard. You sometimes want to overutilize the server and say, okay, I've got a server, I've got 16 gig RAM, I've got 8 CPUs. I could run, a operating system per one CPU. So you could virtualize, your 8 CPUs is 8, but you can obviously, times it by 2, then you have actually 16 cores because you have the virtual cores available. And so you could run nice operating systems on one server. But remember, now you're sharing it all together. So now it's about how many OSs can you run. And so in this example here, you would see that we have Windows 10 there, Ubuntu, Red Hat, Windows 10, Ubuntu, Red Hat. These are all different operating systems, but they're all sharing a bit of the resource pool. So this Windows 10 might have, depending on the capacity here, let's say for instance, this was, a total of, let's say, 24 CPUs, right? The memory is maybe 128 gigabyte of memory together in total. If you maybe add all of this together. Are you still on slide 2? Oh man, what's wrong with this network today? So you guys can't see what is virtualization that I'm talking about now. No, we're not on slide 2, we're on slide 5. What is really going on? Anybody can confirm? Can you see my cursor? Can you see anything happen? Or are you all on slide 2? Everybody's on slide 2. What's going on in this? All right. I am gonna have to do the following. I'm gonna stop sharing quickly. Let's do this. Let me not disrupt my flow the whole time. I'm gonna have to share in small windows, small screen, and hopefully that will work. I don't know what's happening with full screen today, um, and then we'll just have to, use it in that sense, because this is really not helpful, to be honest. That it's actually doing this to me this morning, and I have to actually report this to Huawei to say that there's something wrong with the screen sharing today. They might have to look at the cloud side of WeLink and see what's going on, why it's doing that. I'm sure it's not on my side. If it's on my side, it might be from my interfaces, but I doubt it's that. So let me just see now. All right, can you see my screen now? I made it smaller and not full screen. Any update? Yeah, let me just do this. You should probably still seeing the forest, yeah. Okay, I'm suspecting I need to do something. Right, so let's see. I am gonna have to just do the following. This troubleshooting today is really not helping me. um, so I'm gonna check now what's going on. For all the days. Okay, let's see now. Right, just give me 1 minute. I just want to check something here. There is something weird going on today. Right, so I'm gonna do the following quickly, just see what happens. Right, probably you can see something now, because now I've just disabled something just to see if anything happens, any changes. Nothing still? Yes, but they are small. What are you seeing? You seeing the slide, or what are you seeing? Okay, let me just check again. Okay, I'm gonna just double check. Far away, but they are small. Yeah, there's something really going on. I'm gonna have to run Wireshark just to double check what's going on. Right, so I'm gonna just say PowerPoint itself and see what happens. Okay, last time. What do you see now? Right, so I'm not gonna go full screen. I think there's something wrong with the full screen. It could be the resolution or something. So everybody could see objectives now, right? Okay, good. Unfortunately, I'm gonna have to now use it this way. Okay. which is really terrible. But hopefully I don't even want to go full screen because then I'm going to cause problems again. So I'm just gonna go through this way. Okay, so we look at basically the objectives which we've covered, and so we'll just go back to our part where we spoke about virtualization. Slide number 3, and then left pane is cascading slide up to number 7. Yeah, that's what you're supposed to see because I'm not sure why it's not allowing me to go full screen, which is obviously using the PowerPoint. Just something weird this morning, but I'll figure it out. Okay, so you can see basically that if we combine, 24 CPUs, I'll probably use Huawei's annotations because I know there's annotations here built in. So that will probably be my best bet now to use. And so again, when we look at it, you have, your CPUs, you have your hard disk, you also have your GPUs, and you have your disks, right? Your hard disks, and so your disks again could all be shared together, instead of one disk, one drive. And so again, that is where we look at combining all of that together, sharing from that 24 CPUs, across the different operating systems that need it. Just want to double check if my recording still runs. That's perfect. Okay. Right. So that would be that part. Now, if we have to move on to the next slide, which I'm just not trying to see that I can just move to the next slide without affecting the flow. Right. So when we look at virtualization again, um, we have this problem where, when you look at virtualization, you have a physical server, right? And the server basically have an app, right? And so all this app basically could be what your operating system, your host would host, and your hard drive, your memory, your CPU would all run in that. Now, this is basically your old way of how we used to do things, right? You have your physical server, you have run any type of operating application on it, and now you have this particular part on this side here where you have your virtual machine that now runs a guest OS on top. And it also runs a guest machine, a VM machine, on top of a sort of hypervisor, right? And so this is the three layers that's added with virtualization. So that's the difference that you see normally when you have your normal operating system and you have the guest OS that now basically, and the virtual machine, guest machine, and the monitor hypervisor that runs with that. And so that is the layers that's created with virtualization. And these are probably the important concepts. So again, your hypervisor is that kind of software layer or machine monitor, virtual machine monitor, which the term in Huawei would say VMM, which is virtual machine monitor. That monitors the hardware resources that it actually gets from your memory and your CPU. And then you have a guest virtual machine that runs from that hypervisor, that would run sort of, let's say, almost like a local kind of server. And that server would then allow it to actually run normal guest OSs, and then you would have your application on top of it. So it looks like layer that you stack on top of it, but that's ideally what you would see in virtualization, what you can do with virtualization. Right. Now, if we look at slide number 7, we now have, and I just have to clear my screen, we now have the history of virtualization. And so the history of virtualization started in 1964, and that is when you had IBM that started to explore virtualization on using mainframes. And then we also have IBM that launched virtual machines running on mainframes in 1972. But if we have to move on further now till we now where we're at now, we could see that in 2008, Microsoft added Hyper-V inside a Windows Server. So a Windows Server, which would be a guest OS, was added virtualization technology in order to virtualize some of the hardware. And in 2008, we had the Linux container, LXC, that was launched. And then later on, Red Hat and many other people jumped on board using KVM as part of the virtualization option for their servers. And so these are all cloud providers and many providers that started like in 2011, sorry. IBM, Red Hat, HP, and Intel, they formed this virtualization alliance in order to accelerate the KVM adoption so that a lot of vendors would adopt their strategy and use the KVM adoption for virtualization. And in late in 2013, there was the talk of Docker that launched, and Docker is still being used today as a container technology. And then later on, we have Rocket that also started. But again, these are just the history of virtualization, how you could virtualize certain things. Right. So let me just clear. And so when we look at the the different types, now these are the common types of virtualization. And so you have your full virtualization, which normally looks at, taking all that resources and fully virtualize it, in a sense that you want to make sure that the CPU, your memory, the input-output devices, can be modified without modifying the hardware, and the guest OS, right? And so you have the full capacity of that virtualization available to you. That's the one type. The other one is using para virtualization, and here you're just using the CPU and memory and the guest OS to virtualize your input output devices. So the guest OS needs to be modified to coordinate with the virtual machine monitor, which is your hypervisor. And so your para virtualization again provides high performance, but poor compatibility. So that's a difference. And we'll look at that now in detail. And then you have your hardware assisted virtualization, which is more, there to help the hardware. It's more for compatibility. Your guest always won't need to be modified because it's a hardware assisted. And this basically, eliminates the differences between, your software virtualization, or if you have hardware virtualization. So this is the three different types. When you look at full virtualization, this is where you use the full resources, you use everything, you virtualize your memory till everything, till your CPU. Para again, you just look at virtualizing your CPU and memory, and the guest OS then virtualizes your input output devices. So normally you would have a virtual mouse or virtual keyboard depending on the type of virtualization that's created. And then also your hardware assisted one is then basically just the help of the hardware, and how compatible it could be. Right, so just to clear all of that again, and go back to this slide here. So now we have characteristics of virtualization. What makes virtualization stand out? And so to point it out, you would see that when you look at virtualization, you can have multiple VMs that can run concurrently. Concurrently means they can run all at the same time, on the physical server. And so you have your hardware there, and you have your VMs running on top of it. And this is the partitioning part of virtualization. You also have, encapsulation, where the virtual machine, can be encapsulated into independent files. So when you need to migrate a VM, the ability for the VM to be moved to another server is possible. Or you can move a copy of that VM, and you can do like encapsulation. You copy that file, that virtual disk file, and you migrate it, or you copy it, moving it to another server, or you archive it. You can do that. That's one of the characteristics of virtualization. So the VM operating environment can be encapsulated into an independent file. And so that independent files, normally you could call it a VM disk, because it's a disk, but it's also stored in a different type of format. And then you have isolation. So if some of the VMs fail, and so this is what you will see in virtualization, is that VMs can run on the physical server isolated from each other. So if this VM fails, it's down, but these would still be able to run and operate. So you don't have just one operating system on one server running, you have there's availability, high availability. If one goes down, there's backup, depending on if it was clone copies of each of the virtualization operating systems. You also have hardware independence, and that means that you can actually run a VM on any server. So you can actually move a VM to another server, um, you know, depending on how you do it. It would obviously be just the hardware that needs to work with. And this is where we talked about the previous things that I talked about, the different types of virtualization types. Full virtualization, para virtualization, and hardware assisted virtualization. And so again, these are many ways of how you can define the characteristics of virtualization by saying you can use a VM, and then you can move it over to another server. You obviously have to stop the VM from running, because there's obviously certain needed things that need to be stopped, and then you can copy and move it over to another server. Right. So just erase the clear all. Right, so now we look at advantages. All right, what's the advantages of virtualization? The one thing is that when you look at virtualization, you have, um, they are obviously decoupled from servers. That's one advantage, which means that if something goes wrong with that server, you can obviously migrate to another server before that server fails. That's one thing you can do with virtualization. And you could be running a VM that runs a web server. It could be as big as a database. It could be as big as running a cloud provider. You're a cloud provider and you run that on a physical server. Those are important concepts. So the migration, the scaling, and integration is all easy. And then obviously your standard virtual hardware consists of files, so it's files that you can easily move. So your security is less work because you just move that virtualization file. That file contains all the configuration for that virtual OS to work on another hardware. And that's the beauty and easiness of it. But before we had that, we had these problems, right? We had the OSs that were bound to physical services. You couldn't move, you couldn't install Windows onto another server because it needed a certain type of requirement. So remember, I spoke about the x86, sorry, x86, and you had the x64. These all different architectures, and so these in the past used to play a big role when we want to install certain OSs. So let's say you want to install Windows 7, which obviously is not supported now, or Windows XP even. You needed to have a certain architecture that supports that. And so if you had to install Windows 7 on x64, it will never happen. Well, Windows XP, yes, but you needed to install it on an x86. And so again, that made it that it bounded to a physical server or to a PC. And so that was before virtualization. Migration was difficult and also unreliable, and it is still today. And scaling is hard because you can't scale this Windows onto another Windows because it might need certain resources for it to run, which it had on the previous hardware. And servers take a lot of space, and also need to be housed and maintained. And this is basically why we have the notion of moving away from what it was previously. Right. Just clear again. Now, when we look at certain virtualization issues, there's certain issues that arises also with CPU, right? Because remember your CPU is being used a lot, and so the CPU needs to simulate a lot of things, right? Send instructions. No voice. What's happening now again? Can you guys hear me? Okay, so it's one of the students. Just double check. Okay, so you guys can hear me. All right. I just wanted to check if everything works fine. Okay, all right, so that's fine. Um, okay, so again, let me just erase that. Virtualization issues arises with certain things, and I'll just continue now. Okay, so it's also sensitive. Many instructions are sent and can be read and write to certain resources, which are normally sensitive because remember you're exposing your physical CPU, your devices all to this particular virtualization technology. And so again, you have privileged instructions that will be sent, which means almost like root permissions or administrator permissions. And so many of these instructions are privileged instructions which can only be executed at a higher level or kernel mode of the processor, right? And that is basically why people would normally tell you, and I think nowadays, if you heard about the talk about Docker, um, which is obviously virtualization technology. Normally, you wouldn't just download a Docker container and just run it on your PC because you need to scan it for behind hidden files and stuff like that. Because some developers would maybe put in certain code in there, and you would just install it and run it, without running it in a sandbox on your workstation or your PC. And so again, because it has this high privilege level, it can integrate with your kernel and your processor. And so again, that is basically what CPU virtualization resolves because when CPU sends instructions, it needs to do all of this, right? And so the virtualization actually handles all of these information, all of these sensitive instructions. It also allows you to have multiple VMs to share CPUs. So you have your VMs that can actually access that CPU without needing to, go through a different kind of process. So CPU virtualization uses this time interruption mechanism, similar to what's used in OSs or operating systems. And what it does is it sends this instruction, to allow it to schedule resources based on a kind of a policy that it uses. And so what it then do after that, so I'm just going to erase quickly again. It creates this kind of layer, right? So you have this kind of setup where you have, the way CPU virtualization works. You have this ring kind of technology, and so how that works is the following. So what you will see is normally is that when you look at your CPU, it has different architectures that you see in front of you, and so the different architectures allow you to really see in detail how the VMs operate and how it works. So you have this thing of no virtualization, which I'm just going to use the pen here. No virtualization, which basically is how your CPU works without any virtualization, right? Your operating kernel sits at ring 0, which is the highest, right? The root mode is obviously 0. So it's the highest level, and so what it will do is it obviously has the highest privilege. And then your user applications normally run in your ring 3. So whatever you run, like your Word, your Excel, your PowerPoint, your web browser, they normally run under ring 3, under the CPU kind of processes, how the CPU works. And again, this is the least privileges mode, right? So this is when you have your x86, no hardware part, no virtualization. When you look at full virtualization based on binary translation, and this is now where your VVM. Now remember when we said the VVM, it's actually your hypervisor. So this is your hypervisor. So it could be your hypervisor, which in most cases is either your Hyper-V, it could be KVM, because remember we'll talk about KVM in detail. It could be any of those particular technologies we'll cover later that would run here. And so they would be on the ring 0. That's why we said to have this um, access to the hardware in a way. And so again, it sits between your guest OS, which would be running a virtual machines operating system that you would run here. The guest OS again could be any particular guest. It could be a particular software that you would need to run and virtualize certain things. And so that's where it sits. And then your virtual machine monitor then translates all this guest information, right? You can see here, it translates all these guest calls into the hardware to form this host OS, so it can understand and manage how this whole translation works. And so what a guest always would see, then it believes it will run on physical hardware, but it's actually running in a virtual environment created by this VM. So the guest always don't even know that the VVM controls how it runs, because the VVM is the monitor or the hypervisor that allows the guest always to operate. So your Windows here would use, let's say this is Windows here. It would use the CPU, the memory, and everything else, without knowing that it's using actually it's running on a virtual machine. It will think it's actually running on hardware. It will think it actually have access to the real CPU, the real RAM, and so forth. And that's kind of what the VM creates. It creates that isolation, or that call it that believe that actually it runs on ring zero when it's not, right? The guest always wouldn't even know it's on ring one. And that's the whole translation, or call it a virtual assistant based on binary translation mode. And so the user instruction, when you run an application, it accesses the hardware, not knowing that the guest OS needs to go through the VM, right? So it accesses the hardware because the hardware is accessible now through the job of the VVM or the hypervisor. Right. Now, when we look at hardware assisted virtualization, this is now full virtualization. You have the hardware that basically now, it's there to support, the whole virtualization. But now your VVM, remember your hypervisor, can now operate at a new level, right? So the VVM now operates at a new privilege level, as you can see here, which is ring minus zero. So you can't see there's zero, which is the guest OS. So this is now minus, call it minus one, because we're going negative. So the root mode operates here in a ring mode minus one, right? And so what it means is that it allows the guest OS to run on ring zero. So the guest OS now fully, almost like if you can see here in the hardware, in the no virtualization mode, we had full access to the hardware, right? When you don't virtualize. So here again, you have your guest OS now running fully, attached to the hardware. So it can now actually use the hardware as much as it can. It can actually scale up more CPUs, more RAM, because it doesn't depend on the hypervisor to actually give it access to the hardware. And so this is basically the elimination of the performance overhead, which we saw here with the VM on ring zero, the virtual machine monitor, sorry. And so it eliminates that overhead, and it allows more instructions and operations to be run by the guest OS here, directly to the physical hardware, which is obviously the CPU, RAM, your GPU, and your hard disk. And that is basically the three different ways of how a CPU gets virtualized. Okay, so we're still just talking here about the CPU sending the instructions, but these are the three ways. It's either it sends it the way you install it just on your Windows, on laptop, and it doesn't actually need any virtualization, so it just goes on ring zero and it sends instructions. That's either number two, where you have a VM running, but the VM runs, with a controller, which like VMware, KVM, Hyper-V, Oracle VirtualBox, that would be under that hardware structure. And then you look at this one here, where you have now, this whole thing where it's on minus one, a ring, and then again it basically gives the guest always full access, to the hardware. So that is kind of the whole three different ways, how this would work. Now, each method that you can see has its own benefits. It's also suitable for different scenarios depending on the requirements. So, do you need more system performance for your hardware? You would have a different method applied. Compatibility or overhead, depending on that. But the preferred one normally is the hardware assisted full virtualization. That is the preferred way of how you want to get your best performance out of your CPU. So it can actually access the hardware. You remember your CPU works close in hand with your memory. And so these two needs to be close, and not have this gap in the middle as you see in the previous one. And so that allows it to directly execute the code on the processor, without needing to go through a emulation or translation. So remember when we talked about, I didn't get to that part, but you have something called emulate, right? You can emulate, or you can, I think the other word is not virtualate, emulate and simulate. So you have emulate and simulate, and all of these to emulate means you obviously emulating, like when you play a game, you emulate something on a Windows, or you simulate when you obviously have like Packet Tracer or the ENCP of Huawei. So that's the two ways, but you still have to run with a software that needs to like access the hardware in a way. Now, obviously, with this, you don't have that emulation process, so that's out of the way, and that's kind of the difference. Okay. What does the ring means? Because you see the rings. The rings obviously refers to the privilege levels architecture of these x86 CPUs. We're talking about these type of x86 CPUs that obviously has these different rings, and that's there to protect the data and functionality from faults. So the rings are there. It's a layer of protection, so that you don't have malicious software running on the operating system. And so basically, it has like a protected ring. These rings are almost like little firewalls. That's why you'll see the user application here is on ring 3, and obviously ring 2 and 1 would protect the user, because it will obviously check that you can't execute certain code before you get to the kernel, right? So that's the whole thing. And so ring 0 has the highest privilege. Ring 1 and 2 are normal, the intermediate way of things. And so ring 3 obviously is the least privilege level, and that's obviously where your normal regular applications would run, interacting with the CPU. So yeah, that is basically just to cover you on this part. All right, I wanted to just explain this better. I couldn't do it full screen, so at least you can see that, but I'm gonna have to now clear the screen, otherwise you will see the same on others. All right, so let's do that. All right, so when we look at the mappings between CPUs and virtual machines, okay, so again, when you look at a two, you have the following. So you have a server that sits here, which you can see here, this is a server. And so the server then has like 4 CPUs. So this is a CPU, that's a CPU, that's a CPU, and that's a CPU. And so what happens here is that the CPU can obviously be broken down into, virtual CPUs, and that's obviously where the kernel now steps in. Remember where we said this whole ring kind of part. But a kernel then again, which is the physical kernel, then obviously creates these threads, and that is where you have from one CPU you can have 2 CPUs, and you can see the same here with this 2 CPUs, and we can add another layer here, but we didn't add that into this part here. As you can see here, these three, right, are being now virtualized, into have like, two virtual cores of one CPU. And so you can see this one is not being used, right? So that is basically just giving an idea of how virtualization works when a physical CPU has to, go into that mode of, sharing resources. Everybody can still see my screen? Okay, I'm on slide 15 now. Right, so when we look at memory virtualization issues, again, this is now about the memory side. So here we look at, how memory actually plays a role, right? So with memory virtualization, we have the following. So we have, sorry, I just drew something there. So we have the native OS, which is obviously operating systems that needs to make sure that memory gets allocated, and memory blocks normally have continuous addresses. So as an application runs, it just allocates addresses. It's never fixed, and never fixed and puts an address there that can never change. Because remember, memory is random access memory, which means you randomly access an address space. You never physically just stays there. and so it can always change, right? But again, it's there the whole time to address memory spaces so that you don't have problems with unallocated memory blocks being allocated. So you have this look of this where you have two particular virtual machines, VM1 and virtual VM2. And so when you look at this here, this is basically one physical server. So this is the server, and so the server then allocates, memory, right? So you can see the physical memory of, which is PM, which I don't see a PM, is managed centrally and packed into multiple virtual memories for multiple VMs. So you have a VM there, and there's the memory allocated, and so you can see it's randomly assigned, right? And it allocates it as it's required. And so that is basically how your memory virtualization works. CPU more have more work to do. RAM basically just allocates it. But again, that is basically how the two works in hand. Right. So again, when we look at input-output virtualization issues, when we look at all of this, there's certain things that can obviously occur. And one thing we can say normally is that, fusion compute, which we'll cover later on, um, has to do two functions, right? And so fusion compute is this kind of VM, virtual machine monitor, that I've been talking about, which we'll cover later. And so it needs to do with device discovery, which means that it controls which devices can be accessed by VMs, which is now your guest OS, your guest VM. And also it needs to access, your input output ports, and also make sure that the device exchanges data with the memory through the DMA, which is a memory channel. And so again, that is basically some virtualization issues and where Fusion Compute now, steps in, which we'll look at later. So again, when we look at it, let me just clear again, clear all. So input output virtualization can be then be considered, where you have your hardware, between server components and OSs and your available input output processing units. And multiple guest OS can be reused, on these different resources. Also with input output virtualization, you can emulate the registers in memory of devices. So that allows you to emulate certain things, and also to also simulate the device behavior. You would also notice with KVM, there's also something called a quick emulator, which is called QEMU, or KVM. And that is how the hard disk gets normally installed, or kept on the on the server in order to be used as emulators, in order to run our operating systems. So an emulator again, is a device that are completely emulated by the software. So the QME software emulates those devices. And in the IO, so it's virtual IO, virtual input output devices are para-virtualized devices that implements the virtual input output APIs. And then you obviously have your PCI devices that are normally directly assigned. These are just showing you the different ways of input output virtualization with regards to how virtualization works. Okay, let's clear all. Now we look at how does this work with full emulation. Okay, so when we look at this particular graph here, we have three different things that we see here, right? And actually four. But what we'll see from this is that with full emulation, the the emulation uses software, right? Software to mimic the behavior of a specific hardware. So the software is used to emulate the specific device. So which means, let's say you want the hardware to be what? Uh, can't say CPU, keyboard, no. Maybe depending on what type of hardware, right? It will mimic that. Maybe a USB You would have a USB or you would have a disk, a virtual disk, because normally a disk is there to mount an ISO. So you would have a virtual disk drive, which could be emulated for you to run an ISO disk inside that VM in order to install an operating system. That's the best concept I can use, where you could mimic software to do that, right? And so again, when you look at that full emulation, it uses the software to mimic the behavior of a specific device. And so even though through your physical hardware, they might not be present, right? So your physical CD-ROM might not be present, but it can actually emulate that, to be there, so you can actually mount a disk. And so again, it basically interacts with that as if it were real. And so this is basically a full emulation. So your virtual devices are different from physical devices in the system. It can be emulated, and so your VM connects to the hypervisor, or the QEMU connects to the hypervisor, so vice versa. And so this is basically used to emulate by software and doesn't affect the software stack of your virtual machine. So it's nothing to do with your virtual machines. It's basically just this whole emulation. Also uses a native driver. So the driver then basically acts as maybe a disk, CD-ROM disk driver, for you to do that emulation. And then the APIs then obviously talks to the VM in order to emulate that that CD-ROM. Maybe you want to have a CD-ROM that you want to run as a emulation in order to mount an ISO. That's the kind of setup there. With regards to, just erase again. So with regards to the following, which is Vertio, which I'll go through now, is obviously the next part. But I think also, um, you know, your, I think your hypervisor, or the virtual machine or the manager, can create virtual devices that will appear in the virtual machine as the real component. So you could add more things, right? I mean, you can add more network cards, So remember, if you have a VM, just to give you context, what I mean by that. So I hope this will load. Tell me you can see the screen in front of you, which is a black small screen, and it has a play button. If not, then I'm not sharing my screen. I'm sharing a PowerPoint. I forgot about that. Yeah, you can't. Yeah, I thought so. Um, because I don't want to stop sharing now and then mess up my sharing. So because I wanted to show you how virtual machine works, but I think it's fine. I'll see if I can do that some other time. Okay. So again, when you look at that, you can basically, if you look at VirtualBox and all those other things, you can actually use that kind of setup, and that will tell you the whole thing about full emulation. So you basically, when you run VirtualBox, you run VMware Workstation, you're basically running an emulation of your virtualization. Okay. And that's basically where you can create more virtual devices. You can add more virtual switches, and you can even add more virtual network cards. Okay. So that again is a high level overview of how emulation works with input output virtualization, and that's how frame virtual machines interact with the emulated hardware as if they're real components. So you would have, what I wanted to say is you would have a CD-ROM. You would have another network card. You could add up to 8, or whatever you want to add. You can add network cards. You can add more memory. You can add more CPUs. And that's the whole thing about full emulation that you can do. Right. Now, let's look at Virtuo IO. Just erase again. So VirtIO is also a type of input-output virtualization. However, with the virtual IO, you have now, it's a standard way of how you would obviously use the network and the drivers and the disk drivers. But again, it creates that common front end for handling input output, right? So you have this kind of shared memory here, as you can see here, and you have this common front end, obviously driver here. that obviously allows everything to be shared together. So this is this Virtio. I think if you've heard about Virtio, it's probably just virtual IO. And so again, it's how basically input output and obviously everything happens and transfer to physical devices from the emulation. And again, you can virtualize special device drivers. Normally, depending on what type of driver you need, that's what you can do with virtual I/O. And also any driver that needs to connect back to the host operating system that's needed. And so again, it's more just about creating the seamless communication between the two ways of things, back driver and the front end driver, and your application that runs there. But again, this creates an overhead. But obviously, the Virtual aims to reduce that overhead between the virtual machines and the host by creating the shared memory that you can see here, which is obviously accessible by the VM and the host. So the Virtual IO allows the VM which you run, let's say it's Windows, um, and it runs mainly on another host, which is the VVM, which in this case I said earlier could be Fusion Compute, or it could be any type of VVM, right? And so, for instance, Windows running on it would be able to directly use the said memory allocated. That's the whole thing about the Virtual. It allows you to have full access to the memory instead of, requesting the memory still, So that's like a quick transfer between the VM and the host. Also, you have a single one call here. As you can see, it's called a hypercall. That reduce the number of times, you have to read write information between the two. So you have this whole asynchronous kind of communication between the two, the OS and the virtual IO. Um, it's normally aimed to optimize the performance and efficiency of environments so that the software that runs on your VMs can communicate effectively with the host resources. Right, so that's basically the whole idea of this kind of setup here, the Virtual OWL. Let me just clear the screen. And so when we look at, when we have to do a PCI device assignment, so in this case here, we basically now I've learned that obviously we use KVM, and so KVM allows the VMs to use the PCI or PCI Express device on the host machine that's attached to guest OS, right? And so you can see you have your guest OS here, which could be any type of operating system. It could be Windows. I think I need to just change my pin here because I'm writing wrong here. Windows. It could be Linux. It could be any type of operating system which will run this guest OS. Um, depending on the type of setup, in this case. But also obviously after, a device, is assigned, so this is the physical NIC here, how everything gets assigned. So you have the PCI device that could be attached to your physical server. And so that then obviously gets attached through this KVM module that now assigns, how this device interacts with the whole operating system. And so your hypervisor or your VVM really doesn't actually interact or participate in this process. And this is basically the interaction between the guest VM and the device interaction, basically the two. So if you have a PCI device like a graphics card that you want to add to the server, you can do that, and that's obviously how it will obviously just do the assignment in that sense. So this is just the basics of virtualization, just give you an idea of how all these things work that you don't see behind the scenes, and that covers virtualization. Now, I'm just watching time now, it's 10 o'clock. There's different types of virtualization technologies which I wanted to cover, but I think let's take a 15-minute break. The slides is not that long. I'm nearly done unless we can finish because there's not much slides left. And then we can, see if I can continue tomorrow with the next part, and hopefully by then my sharing would be sorted. So let's cover this. Let's continue with this. Yeah. So Zen virtualization again is a way of how you would, also use this virtual machine monitor, right? So the Zen virtualization is a type of, let's say VVM, virtual machine monitor, that loads onto the server through BIOS. So this is when you do this whole installation of, taking an ISO, installing it onto your hardware from the BIOS on the server, like you would install Windows on any PC. But you just install this, and you basically run that operating system, and that basically controls how the hypervisor operates, right? So that's kind of this whole Zen virtualization, which is not really common nowadays. I think most people have moved over to the other type, which is the KVM. And so again, just to give you an idea of where we're going with this, if you ever want to do your HCIP, when you're done with the HCIA, HCIP is mainly about OpenStack and Huawei Cloud Stack. So OpenStack is the open source virtualization, and OpenStack has different services and modules. But I mean, if you want to go into HCIP, you will mostly need to understand OpenStack and how it operates with the cloud stack. And that is all these services all combined in how it uses the virtualization. Okay, so that's just some kind of inside info if you ever wanted to figure out what's the content exam of HCIP. So again, when you look at KVM, it's a kernel-based VM. So it's a VM, right? And it's basically there to run on Linux. It uses Linux to perform operating system operations. Um, the task, how it manages the memory, and the interaction with the hardware devices. It's open source, and it was integrated into Linux and kernel in 2007. KVM also is a Linux process scheduled by the CPU, and it runs in the kernel space, right? So it runs on the kernel space, which means it runs on, I think, ring 0, right? And it provides CPU and memory virtualization. It doesn't perform any simulation. So if it doesn't perform any simulation, it means that it runs, the QEMU is the simulation part that runs in the user space, where it provides virtualization, emulation of hardware input. So again, this is just giving a KVM, yeah, and how the CPU operates. So you will now have an idea of why, obviously, KVM is needed, because you can see here that it runs in the kernel space. Also, it doesn't do any simulation, so it doesn't fake anything, so there's no simulation. It runs the QEMU emulator, which is emulation. EMU stands for emulation, in the user space, where it provides the virtualization and the emulation of hardware input output. Now, just to give you an idea of the two versus the two, let's clear again. So with Zen and KVM, you can see basically differences. One, Zen obviously has, assisted hardware, and then the Zen here, which is obviously how the two works, and the hardware drivers. When you look at KVM here, you have the hardware, you have a Linux OS, but you have KVM here running, inside, the kernel, right? And so again, it has the access to the hardware drivers right here, instead of where it has this overhead, where Zen still needs to interact with the hardware. Linux already has access to the hardware, and KVM is just the module that runs, and KVM then allows the QEMU emulation to run, straight from KVM, which is obviously straight attached to the hardware drivers, and there you can run your guest OS. You can run your Windows here, or you can run your other Linux, depending on what you run here. You can do that, right? So that's the difference between the two. In many cases, KVM is still the preferred way of how you would do virtualization, because you want to remove all the overhead, right? And then instead of using Zen. So again, with KVM and QEMU, the emulator, you have, in KVM virtualization, where it virtualizes CPU and the memory, and that's KVM's job. but QEMU virtualizes your input output devices. So that's how the two works hand in hand, right? And so QEMU is the software-based open source emulation software, and so it emulates all the resources required by VMs. So your CPU, your memory, your input output device, the USB, virtual USBs, and network interface cards. It emulates all of that. Whereas KVM just virtualizes your CPU and your memory. Right. And that's how the two works hand in hand. You have your KVM, virtualizes that physical device. Um, the difference between Zen and KVM. So it's the overhead. The difference between Zen and KVM is the overhead that with Zen, you have Zen that still has to interact, with the kernel, still interact, has to go through. So you're trying to remove all the overhead. That's kind of the difference. They both have the same technologies, and obviously KVM uses the emulation. Zen, I think, is more about the simulation kind of setup. I haven't actually seen Zen run QEMU. So that is basically why you prefer rather Zen, KVM than Zen. Zen is also an open source way of running things. I think Zen was used with Citrix. And Citrix is where you could basically run an application on your desktop, and you would basically connect to that application, via your desktop to a virtual machine Windows that sits out there on a server. But again, it all depends on, the needed and the use case. So again, not saying Zen is wrong, but I think it's the way it interacts with the hardware. And you can see here basically that the QEMU emulation actually directly connects to your KVM Linux kernel, and then you have the hardware. So KVM has that kind of root access, or that -1 ring in a way, and as you can see here, because it obviously provides QEMU ring 0. If you can see what I mean, does that answer your question? Because I'm talking about the CPU rings now, in order to just explain that a bit better so that you have an idea between the two. So if I go back to Zen and KVM, you can also see here that there's your hardware drivers, and you have this overhead of Zen. And you can also see that, with KVM, there's no overhead, right? I know it's a bit complicated, but just think of the CPU rings. If you think about the CPU rings, you can see basically why KVM is preferred. It's that part that I covered previously, which is where did I have that slide? Yeah, this part. Remember where I said about the ring? So the root mode, which gives you more hardware, full assisted virtualization. And we have the ring 0, we have the full virtualization based on binary translation. So ignoring and moving away from that translation and that simulation, you have this kind of best preferred way of setup. So I would say Zen would fall under this, and then KVM would fall under this. Okay. So it's more about how the CPU, because the CPU is very important when it comes to virtualization, and it plays a big role on the two. All right, so I think that is the part that I want to cover. So again, KVM is the virtualization solution, as KVM virtualizes your CPU. Okay, so I've covered that now. So I'm just now going over that again. And so again, here you can see the working principles of KVM. So again, here KVM basically is a module in the Linux kernel. So it's a module, right? And so again, just keep in mind, it's not a virtual machine monitor really. It's a module, right, in the Linux kernel, and it runs in the Linux space. QEMU runnings in the user space is used to virtualize input-output devices. And so after the KVM module is installed in Linux, there are three modes. So you have your guest mode, the root mode, and the kernel mode. So these are the guest mode, the user mode, and the kernel mode. These are the different modes after it's installed. And so the kernel mode could also be here, depending on how you obviously install it and at which level, right? So you have your virtual machine here running, which, like I said, it's Fusion Compute in this case, because we'll get to that. Fusion Compute, and Fusion Compute would run there. Well, not really Fusion Compute, but we'll get to that. But that's basically the space we're heading towards. And then again, it would obviously interact with, whatever local input output device is needed, whatever library is needed, and then QEMU would run the emulation. So QEMU would essentially run a typical Windows operating system or Linux, depending on what's needed. It would run that virtual machines. And so if I go more, just a bit further, um, I think the slide was cut out. This was just explaining the working principles of KVM. And I think the slide was removed because you're probably not getting this in the exam. So I'm not going to show you this, but it's just to show you basically how the whole principles works of KVM. And then the last slide is just to give you an idea of the virtualization platform management tool, which is libvirt, which is part of Linux. And so again, it's basically there to allow, your Linux KVM module to operate through libvirt, which is the library for the virtual resources. And so libvirt is basically used to interact with sort of a management tool. And so again, it's basically where you have KVM, Zen, VMware, and Hyper-V all using that kind of library in order to create this whole stable software layer to manage the different methods of the virtual machines in many cases. And so this is basically just the libvirt, which is part of this whole process. Okay, so that is basically the basics of virtualization, why it's important, and where we're heading. Okay, so let me just clear my screen. There is sorry, quizzes here. So the one quiz is in full virtualization, the VVM, which is the virtual machine monitor, is used for CPU and memory virtualization, and the guest OS is used for device input output virtualization. The guest OS needs to be modified to coordinate with the VVM. This method provides high performance but poor scalability. Is this true or false? I think you guys have the answers, because I think if I move this up, you will see the answer. So the first one is false, because remember, VVM is obviously is used for CPU and virtualization, but remember we said that the guest OS is not, it's not really used. It's basically QEMU. But again, we're basically referring to KVM and QEMU in this essence. And obviously this means that the guest OS doesn't need to be modified. So that's the wrong part. And so that's why it's false. And then here, libvirt is a virtualization library on Linux. It aims to provide universal and stable software layer to manage multiple virtualization modes for virtual machines and PMs, and supports remote management, and that is true. Okay, so those are the two quizzes. And so again, to summarize and to end, obviously we learned about what's the value of virtualization, the different technologies, the basic principles, and also how the whole virtualization works with regards to how why we use KVM instead of any other things. Okay, so I think students, that is it for today. I just want to take quick attendance. I know I have my screen and everything else hasn't been well today, but I think I have a recording of 1 hour and 8 minutes, so I'll see.